Welcome. Today we're going to talk about bagging and boosting. These are methods which are kind of different than what we've done so far in the sense that previous methods are totally different from each other. For example, logistic regression is one type of classifier, SVM is a totally different type of classifier, decision trees are another type of classifier, and so on. Whereas today, bagging and boosting are ways that make existing classifiers better. So for example, suppose you have some decision trees. Well, these allow you to make decision trees into better decision trees. So yeah, these are the two methods we're going to talk about. They're relatively different between the two of them, so we're going to focus on them one by one. The first one we're going to consider is bagging. Bagging stands for bootstrap aggregating. So maybe you know what aggregating means, putting things together and combining in some way, but the word bootstrap in this context might be a little bit less familiar. And bootstrap refers to bootstrap sampling, which is a classic technique in statistics. So let's try to build up some motivation as to why this is going to be a useful technique. So the main idea behind bootstrap sampling or bootstrapping is the idea that somehow repeating something many times and taking the average will reduce the variance of that. Now, this is great if you have a lot of data. If you have a lot of data, then you can just average a bunch of different things, and that's great because it'll reduce your variance a lot. But if you don't have a lot of data, sometimes you can still do things by these tricks known as bootstrap sampling, where you kind of create more data in some way. It's not going to be perfectly principled in sort of finite sample settings, but it's still going to work pretty well. Okay, but that's just a high level. Let's get a bit more precise. I'm going to describe to you one specific setting in which we're going to look at how bootstrap sampling is useful, and then we're going to take it a bit more broad, back to bagging in the context of machine learning algorithms. So again, let's focus on a very basic statistical setting first, just to illustrate this principle. So we're going to imagine that there's some data set, x1 through xn, let's say, where these are drawn according to some distribution, let's say a Gaussian distribution, but it doesn't necessarily have to be. They're all drawn IID from some distribution with mean mu and variance sigma squared. And the goal is to estimate mu. So classic mean estimation problem. So now, of course, the obvious way to estimate the mean of a random variable, given a bunch of samples from it, is just to take the empirical mean. So we'll use the estimator, mu hat equals 1 over n summation of xi for, say, I equals 1 to n, if there's n samples. That's good. Let's see some properties of this estimator. Well, a very simple thing, which I'm not going to work out for you. You should know why this is. If not, think about it a bit more. But by linearity of expectations, the expectation of this random variable is equal to mu, the true mean. But more importantly, and less trivially, let's look at the variance of this random variable, of this estimator. The variance of this estimator is just going to be variance of the quantity on the right-hand side. And let's expand this out. So the nice thing, we'll recall some basic rules of variance. So when you have a constant inside the variance, you can pull that out and it gets squared. So this becomes 1 over n squared variance of the summation. And now the important thing that we're going to do is, again, we're working in the IID setting here. We're assuming that these data points are drawn independently from this distribution. And the nice thing is that when these variables that we're summing in here are independent from each other, then we can pull out the summation. So this is the sum over n elements. And so therefore, this is equal to 1 over n squared times n times variance of xi, where xi is just an arbitrary one. So let's just say is equal to variance of x1. And then just combining this, we have 1 over n, and the variance of x1 is going to be sigma squared times sigma squared is equal to, I guess, sigma squared over n. So we can see that somehow by averaging these data points, we managed to reduce the variance of, we got a variance of our estimator to be sigma squared over n. That's great. Now the question is, what if this isn't good enough? What if this is still too much variance for whatever application we care about? This is not a great estimate and we want to do better. Well, one thing we can do is, if we had the luxury, well, one thing we could do is just do this many times with independent data. For example, like let's suppose we have, say, we have bn points, which are all IID from this distribution. So let me just draw that here, n mu sigma squared. So if we had this many data points, then life would be really easy. Let me sort of belabor the point and write out exactly what we would do. Well, what we would just do is we would we would do a bunch of different estimators. So what we would do is say mu hat I. Let's index it a different way. Let's index this with j, I guess. So we're just going to split our data into j different parts, or sorry, into b different parts, and each one we have a different set of points. So let me like let me write it like this. So we have, say, s1 equals, say, x1 through xn, and then we have s2 is equal to, say, xn plus 1 to x2n, and so on. The point is we have bn points, so we make s sub b subsets of this, each of which are disjoint from each other. So this is going to be x sub b minus 1 times n plus 1 all the way up to x sub bn. So yeah, the point is we're just splitting our data set into a bunch of independent disjoint partitions, and then we just define an estimator on each. So that is, this will just be 1 over n summation of over, let's say, z in s j z. So this is just saying that the jth estimator that we're going to use for this mean is just going to be summing up, averaging the points within the respective set. So okay, that's good. Now we're going to compute a bunch of different ones, and what we can do after all of this is we can just average all of these estimates we had. So we can do something like this, say mu hat average. This is equal to now the average over these different sets here. So mu sub j hat. Yeah, and we just average them. So now if you do the analysis, then first of all, it's not too hard to see that the expectation of, sorry, this is terribly written, of mu hat average, this is going to be equal to mu. And furthermore, just doing the variance analysis, very similar to what we did before, we're going to get something like the following. Let me just do it out here because, again, there's like a crucial point that we're going to use. So once again, we can pull out this, sorry, this is a different thing. So this is just by pulling out this 1 over b, then it becomes 1 over b squared. And then the second thing, again, we're going to use is the fact that each of these summons are independent of each other. Each of these things works on a disjoint set of samples. So therefore, these estimators mu hat j for all j are going to be independent of each other. And therefore, pulling out this summation is allowed because they're independent. So that gives us a factor b because there's b things in the summation. And then here we already calculated the variance of each thing. This is just going to be sigma squared over n. So this is equal to sigma squared over n times b. So what can we see here? What can we conclude? We can see that if we got a factor b more data, then we would be able to reduce our variance by a factor of b. So this is great because we reduce the variance a lot if b is large. However, this needs a lot more data. In particular, it needs b times more data. And this is not great if we're in a settings where we are data constrained, of course. You don't always have limitless amounts of data, so this is not a luxury that we can always afford. Now, instead, what bootstrapping does is it does something, it generates these sets, but instead of making b n times more points, it just resamples things again and again, and it does sampling with replacement. So let me, I'll just write it here and then we'll discuss what that means. But bootstrap sampling, this is, yeah, it's roughly the same as sampling with replacement. And let me explain what that means. So let me, for example, let's just start with a small data set. So suppose we have a data set, which is just 5 elements, let's say, x1 through x5. Let me just write it out fully because it's small. x2, x3, x4, and x5. Now, what we would do is we're going to make some subsets, like again, as before, we're going to make b different subsets, each of size n. But this time, we're going to just repeat elements from this in the following sense. So say S1, we're just going to pick, we're going to pick 5 elements at random from this, but we could pick the same thing. So for example, I pick one at random, and it happens to be, say, I don't know, x3, that's just chosen randomly. And now I just repeat that again. I pick another thing from this uniformly at randomly, and I pick maybe x4, and I do it again, and maybe I get x1, and I pick it again, and maybe I get x1 again. So notice that it can pick the same thing multiple times. That's why it's called with replacement. And then maybe you sample again from the set, and you get x4. So yeah, this is a bootstrap sample, where you essentially sample with replacement from the set. That's one sample, well, one set of samples, and you do it again. S2, say this becomes, say, I don't know, x5, x5, x3, x1, x2. So you can see we have some repetitions. We have some which never show up, but that's okay. Both are fine, and this is just bootstrapping. So now, and we repeat this all the way up to, say, SB, which is drawn, again, the same way, uniformly at random with replacement. Okay, so now we just define things as we did before. That is, we have, what is it? Mu hat j is again equal to, this is exactly what I wrote above, summation over 1 over b. Oh, sorry, no, let me say this, 1 over n, summation of z in sj of z. So this is the exact same thing that we wrote before. And we have, again, let me just repeat this, mu hat average is equal to 1 over b summation over, let's say j equals 1 to b of mu hat j. And this will kind of be our final estimate of the mean, this one right here. Now, the thing is, how can we just do the same analysis we did before? How do we analyze this? Well, you can still compute the expectation by linearity of expectations. This is still going to have the same expectation property, that expectation of mu hat average. This is going to be equal to mu. But the trickier part is the variance. This is not so easy to compute. And the reason is because of the fact that this actually has this loses the key independence property which we used earlier. So remember I said when we are computing this variance here, we can pull out this constant, that's always allowed. But then when we pull out the summation, that was using the fact that the terms here, these xi's, are independent from each other. And similarly, when we pulled out the summation here, that also used the fact that these sets of data that we were using are disjoint. That is, they don't overlap at all. So we used independence properties twice when deriving this type of variance bound. So therefore, we can't really just straightforwardly compute the variance of this resulting estimator. So that's kind of the bad thing. These are not independent. And what do I mean by these are not independent? I mean, neither these samples are independent from each other within a set, and these estimators are also not independent because they draw from the same data set. So those are both bad things, these two independence things, but it still works anyway, in the sense that this is still seen to give, in general, better variance estimates of the parameter mu than you would expect in sort of the worst case, or if you didn't do this in many cases. So yeah, this can be a useful trick. It's also useful for other things besides just getting better estimates of things. For example, it can be used also to generate confidence intervals for various parameters in certain ways. That's something we won't get into. But yeah, it's a surprisingly effective approach to doing statistics in machine learning sometimes. So good. This is sort of the first part. We talked about what bootstrap sampling is and the intuition behind why it helps. So just to recap in a sentence, bootstrap sampling just says you generate many data sets by drawing from the same data set with replacement. And it helps because it kind of simulates this variance reduction that you would get as if the data were truly independent, even when it's not independent. So good. Sampling with replacement and variance reduction. Those are the key points. So, okay, now that we have the bootstrap, let's talk a bit about how this is actually applicable to machine learning. We talked about a very simple statistical setting, but how about more complicated settings, say involving classifiers or regression or something? So yeah, a big problem in machine learning settings is that some approaches are just high variance. And what do I mean by high variance? Well, I kind of mean the following. Consider decision trees are a canonical example of a high variance machine learning algorithm, in the sense that if you split your data into two parts and then you ran a decision tree algorithm on the first part, as well as a decision tree algorithm on the second part, well, in many cases, these will give you very different trees and different algorithms. So let me just sort of summarize that. And I'll use DT to say decision trees. So yeah, this often happens that running decision trees on two splits of the same data set will result in very different trees. And this is kind of, why is this unusual? Why is this weird? Well, it's kind of related somehow to overfitting, and it kind of is saying that ideally, you would want your decision tree algorithm to generate basically the same tree no matter which subset of the data you run it on. This is because it's not really trying to do well on the data set, it's trying to do well on the test data set, which is sort of drawn from the same distribution. You want this generalization property, and if you're kind of getting different trees or different splits or you're getting different classifier algorithms when you run it on different splits of the same data set, this indicates that maybe it's a rather high variance type approach that leads to a lot of different results. So what we're going to do is we're going to use bootstrapping or bootstrap aggregating in order to reduce this variance here. So we're going to use bagging. Now, okay, so a little bit more space here. So how do we use this? Well, it's pretty much exactly what we said before. So step one is going to we're going to bootstrap sample many data sets. And you know how this is done. We just take our data set of size n, and we do the sampling with replacement to generate one data set of size n, which may have some repetitions. And then we do it again b times to make b different data sets from the training set. And this will get us some sets s1 ... through sb. So that's the first thing. And then what the second thing we're going to do is run the algorithm on each, like our learning algorithm. And yeah, this is basically using whatever learning algorithm. Like I said, we could use decision trees, but it's pretty generic in the sense that you could also run linear regression, you could run k-nearest neighbors, whatever you want. The point is, if you do this and you run the learning algorithm on each of these different classifiers, then it'll give you b different functions, which are kind of our different classifiers. Or maybe they're not classifiers. It works in both the classification as well as the regression setting. But either way, we're going to get f hat 1 through f hat b, which are our different classifiers, which are trained on each of these different data sets. Good. So now we went from one, we have one learning algorithm, but now we've got b different classifiers. But we don't want b different classifiers, we just want one classifier. So the idea is we're going to combine these different classifiers together. So this is where the aggregate comes in. We're going to aggregate this. So here's where the name comes in, bootstrap and aggregate. And how do we combine them? Well, it's pretty simple. It's maybe the way that you would expect. So the way it depends whether we're in a regression versus a classification setting. So let's start with the regression just because it's more intuitive maybe. In the regression setting, remember each of these you feed in some x, and it'll give you some y, which is real valued. Well, all you have to do is just average them, and that'll give you a prediction for that points label. So we're just going to let f hat of x be equal to 1 over b times the summation of the different classifiers on that point. Good. So that's easy, and also easy. It's not that much harder to do the classification case, honestly. If these are each classifiers which predict some label for the set, say some sort of something from a categorical variable like 1, 2, 3, 4, well, this is easy enough because we can just pick the majority vote. So f of x is equal to the majority vote. Of these f hat j of x. So for example, if 90% of these predict that the label of x is going to be 1, then f hat of x should output 1. And that's it. That's all bagging is. It's relatively simple. So yeah, you just basically bootstrap a bunch of data sets, you run it on each, and then you put them together in the appropriate way. Good. Let's talk about the last extension of bagging that we're going to mention, which is that of random forests. So random forests are almost exactly what we saw here, but there's certain issues with it in certain cases. So this is like, the way I'll describe it is like bagging, but minus correlations. At least some of them, not all correlations. It's minus some correlations. And it's a very simple tweak to how we would do bagging. And sorry, let me say in particular, let me say this is bagging on decision trees minus some correlations. So now let me try to motivate this. Let's recall how a decision tree makes a decision on how to split. Remember, I'm just going to draw this real quickly. We have all of our points in one node, and then the idea is we pick some feature to split on, say like, I don't know, age, if that's a feature, and then you split on that, and then you have less than 18, and then greater than or equal to 18, and that gives you some classification for these people, these points, and some classification for these points, and then you can split again based on this and this. Say this could be something like immunocompromised, etc. And then this would be no, and this would be yes, and then you split again. And the idea is that, like, yeah, you build a tree by splitting on variables based on various characteristics of data points. That's a reminder of what how random decision trees work. Well, the important thing here that I'm going to mention is how do we choose which to split on? So the way that we discussed last time on terms of choosing how to split a decision tree is you essentially look at all of the different features that you can split on and pick the best. So let me say classic. Look at all features. Pick the best. And I'll put this in quotes because we talked about this a lot in the previous lecture, how to define what it means to be the best feature in terms of like the most informative, maybe in terms of minimizing some entropy or a Gini index or something like that. So that's how we did it before. But the issue is that this can lead to a lot of our trees looking very similar on the same data set. Remember, we were talking about how when we do this bootstrap sampling, that we would have correlations between these random variables, which can hurt us. Well, this generally isn't too bad, but it turns out in this case, if you have, say, one very, very informative feature, which all the points sort of have, which is very informative, and then many other ones which are pretty good, but not quite as good as that very informative one, then it turns out that all of these different trees that you build on the same data set will look almost identical because they're all sort of honing in on that one feature being so interesting. So instead, to introduce a little bit more variety, we're instead going to perhaps limit the number of features that they can look at randomly. So RFs for random forests. Choose random, let's say m is approximately equal to often like square root of the dimension. Features split on best. So the idea here is we're going to limit, let's say here you would look at all D features when you're choosing which to split on, but here you're going to subsample these features and split on the best from within this subset. So often it's chosen much smaller, maybe even sublinear in the number of features you have, say square root D. And yeah, like I said, this can help because it can introduce a little bit more variety and break some correlations. And so that's random forest. It's a very common and surprisingly powerful algorithm a lot of the time. The question you might be asking is whether these things actually work and whether these things help at all. And let's see via these two plots, which have gotten shifted off. But yeah, these two plots show some results. Let me try to interpret them for you. Okay, just focus on the left plot in terms of these top two lines, the black line and the yellow line, and as well as this dotted line. So this dotted line here is the test error when you is the test error when you just use a single decision tree, whereas the black line here is the test error if you do bagging. So you can see that it may be, the x-axis here I'll mention is the number of trees, the value of b basically, and you can see that it jitters around a little bit, but eventually if you take enough, then the error drops below what you would get by just using a single decision tree. Similarly, focusing on the yellow line, you can see that using random forests, it significantly seems to improve upon the baseline of just using a single decision tree, but also improves non-trivially over bagging as well. So those are, that's how it looks on this. And you can see there's some advantage by doing bagging in random forests. I'll also draw your attention to this figure where you can see how this is a random forest, and you can see 3 different lines in terms of how we choose this value of m, how many features we inspect at each split. Well, the one that seems to do best, at least in this very simple case, is the case where m equals roughly square root p. So they use p instead of d for the number of features in each point. You can see that that gives the best test classification error, and that seems to be more significant than how many trees you do, as long as you take enough trees. Good. So this is oh yeah, and I should mention that both of these figures are from the Introduction to Statistical Learning book that we use in this course. So yeah, this is basically it for bagging, and you can see that it gives non-trivial improvements in terms of the accuracy when you do it right, and it's very simple. It can be used very broadly. Yeah, next we're going to move on to another approach known as boosting.